Uh, today's topic is coordinate-wise transformation and Stein type densities. This is the outline of this talk. Let me consider a set of density functions obtained by coordinate-wise transformations of a given density. And let me call it a fiber. And then define Stein type density as a by a functional identity as stated later. And then I will establish an existence and uniqueness theorem of the Stein type density in each fiber. And finally, we discuss application to a rating problem. Here is a picture of this talk. In the space of probability densities, if we are given if the probability density function P is given, we have a fiber by coordinate-wise transformation, and each fiber has a Stein type density. Okay, let me give some definitions. First, let script P be the set of positive and continuous probability density functions on the Euclidean space Rd, such that the mean of each coordinate is equal. The last condition is not so essential. We call a map T from Rd to Rd as a coordinate-wise transformation if it is written like this. So the map T, each coordinate of T depends only on that coordinate. So this is a coordinate-wise transformation. And for each density function P, let me define the P fiber by this formula, script Fp, which is a set of push-forward density of P by the coordinate-wise transformations T. Okay, and there are two remarks here. The set Fp is totally geodesic subset in the Wasserstein space, and the secondary, the fiber has a unique copular density, which is known as Sklar's theorem. And next, we define an energy functional on the set of probability densities. The function is defined by this formula. The first term is negative entropy, and the second term represents the internal energy, where b of x is a continuous function of x. And this functional appears in the theory of optimal transport. And here is a simple lemma. It is not difficult to prove. The functional E has the minimum point in the space P if and only if this integral is finite. If this condition is satisfied, the minimum point is given by this one, the exponential family. And we consider the case here, this condition is not satisfied. The integral is infinite. Then the infimum of the functional E is minus infinity. Here is a picture of our setting. The functional E is not bounded from below on the whole space P, but this functional may be bounded from below on each fiber, because the fiber is a proper subset of the whole space. Okay, this is the problem. To minimize the functional E over the fiber, consider a perturbation of the transformation. Epsilon is the identity map plus some perturbation. Here epsilon is a small number and f is an arbitrary function. Then we have, as epsilon goes to 0, the first variation formula. And so if this term vanishes, then that point is the minimum point of E. Now we define the Stein type density. A density function P is called a Stein type density if it satisfies this equality. This is the first variation. And the Stein type density is named after the Stein identity, which characterizes the standard normal density function. And this identity is used for evaluating risk of estimation and checking discrepancy from the normal distribution. Okay, now to state our main theorem, let us suppose some conditions. First, we assume that the function b is degenerated as follows. Vx is a function of sum of its coordinates, where psi is a non-negative and convex and coercive function like this. And please note that in this case, the integral here, integral is infinite because the function b is degenerated. But this restriction can be relaxed, but we assumed anyway. For the second assumption, we assume copositivity for the density function. Here, for each p, density p, we denote the product of marginal densities by p independent, like this independent density function with the same marginal. Then we say that the density p is copositive if the following inequality holds. This is some infimum of the ratio given by this. And if p is the independent density function, then this quantity is 1, so it is copositive. And sufficient conditions for copositivity are discussed later. Now I'd like to state our main theorem. Assume that the density p is copositive, just defined. Then there exists a unique Stein type density in that fiber. And this is the main theorem. Here is a brief sketch of the proof. Details are omitted, but for uniqueness, the displacement convexity argument in the theory of optimal transportation can be used. And for existence part is more essential, important in this talk. And for existence, we use the copositivity condition. And by using the copositivity condition, we obtain the following infinity, and the problem is essentially reduced to the independent case. This is the rough sketch. Now, we give some sufficient conditions for copositivity. The details are omitted. The notion of positive dependence plays an important role here. there are here I show three conditions on positive dependence, and here is the result. It was known that MTP2 condition implies associativity, and it implies PSMD condition, and finally it implies our copositivity condition. And MTP2 condition is relatively easy to confirm, so this condition, this theorem will be useful. Okay, finally, I'd like to discuss an application of our results. The problem is here. Let x1 to xd be random variables with density function p, which represent student scores on the academic subjects. Okay, and how to classify the students into the superior half and inferior half. The answer, one of the answers is here. Let psi x is absolute function and t be the Stein type transformation of, so the t sharp p is the Stein type density of p. And then define g, random variable g, by the sum of transformed variables. Then our main result implies the following stochastic ordering property. Given that this conditional probability is always greater than the right one. And this, the interpretation of this inequality is the students with larger g are superior. Okay, here is a numerical example. But it is further, it is a little artificial. Okay, anyway, in summary, we showed the existence and the uniqueness theorem of Stein type densities under the copositivity condition, and an application to rating problem was presented. And there are two conjectures and some further topics here, so please, if you are interested in, please ask me. Thank you very much.
So in your ordering, the alpha is an hyperparameter?
Alpha is real, any for. Thank you.
Any more questions? So let's have a speaker again.
Thank you very much.